speakers, which are Sanne Vrijenhoek and Gabriel Bénédict, and this paper was the runner-up for Best Paper this year. And it is called Radio, Rank-Aware Divergence Metrics to Measure Normative Diversity in News Recommendations.
Okay, well, hello everyone, and thank you all for being here. My name is Sanne Vrijenhoek, and I am here with Gabriel and Mateo over there to present our interdisciplinary work, Radio, which is done in collaboration between the University of Amsterdam's law faculty, the computer science faculty, and RTL, Dutch media organization. And first off, I want to talk a little bit about news, because news recommender systems are very extensively studied for their unique characteristics, such as the data sparsity and the very short shelf life of the articles that need to be recommended. But news also has a democratic role to play in society, as what news is shown to the users may in a way shape their worldview and as such also influence important decisions, such as who to vote for or maybe a good cause to support. And gatekeeping what news is shown to the user has always traditionally been done by the newsroom and its news editors. And these people would decide which articles had priority over one another. And news recommender systems would in part be taking over this very important role, but without the means to evaluate them in the same way as we would news editors. Many news organizations are in fact pretty hesitant of adopting this technology. And this is a shame, because a good personalized news recommendation could potentially also do a lot of good. So what we need is a way to evaluate our news recommendations based on their normative diversity. And here we define normative diversity as a news recommendation that succeeds in enabling people to fulfill their role in democratic society. And they could, for example, but not limited to, increase engagement of citizens with the news, and not just with a nice entertainment or sports article that they might want to click on, but maybe by presenting them with viewpoints they have not seen before, or a bit more with local news, or catering to their stylistic or complexity needs. And how we see it is that in practice this could work in the following way. A news organization needs to decide itself what the goal of a news recommender should be. And this does not need to be one single thing, because an organization can have multiple systems running in parallel. And next, the news editors, the journalists, and the data teams need to work together in deciding how this goal could and should be expressed in metrics. And our goal is that with our contribution, we build a sort of bridge between the editorial and the data science teams by, on the one hand, allowing data teams to evaluate their recommendations based on editorial or normative principles, and on the other hand, by providing editorial teams with a bit more understanding of what actually happens within the data teams. And this is where, at least for our purposes, the current standard of diversity falls short. We call this descriptive diversity, which is commonly implemented as an intralist distance. But with intralist distance, there's a lot of questions that pop up, such as, what does it mean for two articles to be similar or different? And is more distance always better? And to paraphrase my philosopher colleague a little bit, diversity is not a concept that stands on its own. It is always diverse in comparison to something else, which means that you actually need to look beyond what is in your recommendation only. And the first two questions have been answered to some degree in earlier work, which were proposed a set of diversity metrics grounded in democratic theory. And it will sometimes be necessary during the rest of this talk to refer back to this concept, but unfortunately, because of time, we cannot go into that too much. But if people are interested, we include a QR code to this paper a bit further on in the presentation. So what we propose as an alternative to the current standard of descriptive diversity is a formalization of diversity based on F divergence, here expressed as D divergence between P and Q. And with this, we look at news recommendation as a distribution of values as opposed to just comparing, for example, mean values. And with this, a couple of decisions need to be made. First, we need to choose what are the relevant features that we want to look at, which could be, for example, the representation of political articles in your recommendation. And this corresponds to our P distribution. And next, we need to decide what we want to compare the recommendation to, which is the, am I still in the right place? Which is the Q distribution. And here you can think that you maybe would want to compare your recommendation to what the user has read before, maybe all the items that were actually available at that point in time, or maybe what was recommended to other users. And lastly, we need to decide what is your expected value range for this divergence score. And this could be based on the metrics that were proposed before in our earlier work, based on democratic theory, but it's also flexible to different or people's own interpretations. And I think in summary, we do not really propose a universal norm for diversity, but rather a procedure for expressing a type of diversity that is expressive of your specific use case and diversity needs. And next, Gabriel will talk a bit more about the specifics of the divergence calculation and our example implementation on the MIND dataset.
Okay, thanks, Sanne. So we came up with some requirements we felt we wanted to have. One of them is not super original. It's just saying, okay, maybe we want to have a traditional distance measure with these three principles: identity, symmetry, and triangle inequality. We'll come back to symmetry in particular. Second, we thought maybe it would be nice if it was bounded by 0 and 1, so that we can compare between different recommendation algorithms and across data sets. And then finally, we thought, let's make it rank aware, because we're at RecSys after all. Remember, this is DPQ, right? So we have a generic divergence between Q, the recommendation set, and P, a certain context. About symmetry, this is a slide borrowed by our VAE friends because they like optimizing directly with KL. We looked at using KL to compare entire distributions, but the problem with KL is that it's not symmetric. So we felt like, let's not use KL, let's use JS instead, Jensen Shannon divergence. And with a particular formulation of it, you can also bound it by 0, 1. Then the most important component is about rank awareness. We have a discount. We thought about, do we use MMR and DCG? Seems like literature shows that people tend to have a scrolling behavior that's rather MMR-ish on news articles. And then importantly are these 3 dots there. With the 3 dots, we mean that if you have click data, then why not implement an algorithm that actually, something like that's click model based, that actually estimates these discounts. Finally, this is what we think is our contribution. So we have a rank aware F divergence, and it's implemented, as I said, with JS as a divergence. The star indicates that it's rank aware with 2 limitations. One is that continuous values must be binned, and then the second one that there is no relation between these categories that can be modeled. We also saw that, we looked at sensitivity analysis. Okay, is it actually useful to make it rank aware? And I'm going to skip through these slides, but happy to answer some questions. Yes, it is useful to be rank aware. And yes, it makes a difference, of course, where you put the cutoff. Is it at 1, at 10, or at n even? I'm going to more or less finish by showing some results on the Microsoft News Dataset. On top, you have some metrics. On the left, you have some newer recommenders first, and then 2 more naive recommendation algorithms. And then finally, at the bottom, you have a table of reference where you can see possible democratic norms that a newspaper can have and the corresponding expected metrics. Now we're going to give an example of how you interpret this table. So in the liberal model, recommendations are tailored to the user's preferences. And so we expect low divergence in topic calibration. And so that's why here NN recommenders win. Now, if you take another example with a critical model, if you look at that critical model, you want high divergence in the presence of alternative voices. And so, by essence, you want high alternative voices in your recommendation set. And here you can see that random recommenders actually perform best. These two facts are very intuitive. The first one is because neural recommenders actually use the history and discovers topics you're interested in, and then recommends you topics you will also read after. But the thing we want to say with this, the take-home message, is not just to say sometimes random, sometimes neural. We really want to say that it's still about neural recommenders, but maybe they can be suitable for certain aspects of diversity, but sometimes they need to be really optimized for these diversity metrics. That kind of links to the next steps. So first, there were a lot of things to extract from these articles. We actually scraped these articles and had to build our own metadata from it. And certain things are hard to estimate. For example, what is this political standpoint of someone that's mentioned in an article? It's not always clear. We also don't define a universal vision of normative diversity. What would that be? We're not really sure what would that be. Does that exist? And then linked to what I said before, a metric, maybe we can use these metrics as losses for recommender optimization rather than just post hoc evaluations. But we felt that this first work was, well, it's not a first work, but at least this work here is important to, it was important to raise awareness about normative diversity first before optimizing for it. Finally, we are fostering collaboration with news organizations such as the BBC, RTL News, and NPO. And this is part of our next steps, and we hope that anybody who is here in the room or anybody else who is listening online, news agencies, we hope we can collaborate and hope to put that in practice. Thanks a lot for listening. Here you can find the code and the paper with this QR code. And thank you.
Thank you very much. So we have a number of questions. I guess you want to switch in answering them. The first one is on the intention behind this. With a normative view, are we adding a new role to news? And what if the role is not actually interesting to the user? What if they want to have their sports news instead of what you are proposing?
Actually, that is one of the models. So this is part of the earlier work. You can have different standpoints in what you want your recommender system to do. And one of them is the liberal model, which quite literally says, sometimes, the user just knows best what they want. If they want to watch cat videos all day, please let them. But this right now is something that happens by default. It's not an explicit choice that a media organization makes. And I think that is kind of what we're going for, to ask also organizations to make a normative standpoint like this and also be evaluated based on that.
Okay, thank you. A more technical question, it's jumping around. How can the diversity metrics also account for the temporal aspect? Especially in news, you want the most recent news. Could the diversification lead to old news being recommended, for example?
So I think there are two things here. One is what we didn't talk into detail about is the context distribution. So to what do you compare to? And that's actually quite complicated, especially when the context is the pool. You can ask, what is the pool of available articles? Is that the past day, the past week, the past year, all the newspapers in the world, just this newspaper? So I think that relates a little bit to the time aspect. I think we don't explicitly model a time aspect, so I'm not going to try to say that we do, but I think that we could use our discounting method also for time.
Thank you very much. There's more questions. Please answer them on the RecSys Hub later on. Let's thank the speakers again. We are staying in the realm of news recommendations and political diversity. Our next speaker is Kartik Shivaram, and he will talk to us about reducing cross-topic political homogenization in content-based news recommendations.
Hi everyone, my name is Kartik Shivram. I'm currently a PhD student at Tulane University, and today I'll be presenting our work on reducing cross-topic political homogenization in content-based news recommenders. And this has been a collaborative effort with Ping Lu, Matthew Shapiro, Mustafa Biljik, and Aaron Carlotta, who's my advisor. So we know that personalized news recommenders build models of user preferences based on prior engagement. And recent research shows that these systems can contribute towards the formation of filter bubbles through which users are overexposed to homogeneous viewpoints. And this type of intellectual isolation can degrade civil discourse, contribute towards the spread of misinformation, as well as cause polarization in social media. So given the mix of different technological, social, and political factors that contribute towards this phenomenon, further research is required to understand specific mechanisms that can cause these filter bubbles and design systems that are more resistant to them. So in this work, we look at a specific mechanism of content-based news recommendation systems that can cause filter bubbles that we term cross-topic homogenization, cross-topic political homogenization. So what exactly is cross-topic political homogenization? So consider users who have diverse political preferences by topic. And as content-based news recommenders learn text features that correlate with user engagement, we find that they can have a homogenization effect by recommending articles of the same political lean across different topics. For example, the phrase extreme right may appear in liberal articles a user has liked discussing healthcare, as well as in liberal articles on immigration that the user has not yet read. But if a user in fact prefers conservative articles on immigration, the recommender may thus incorrectly recommend liberal articles due to the presence of the phrase extreme right. And this flawed recommendation is further amplified when topics are not known a priori, and which is often the case in political news, where detecting emerging topics is a research challenge on its own. And this type of phenomena was also observed by us in a previous study, where we looked at the interaction between simulated users with heterogeneous preferences and political news recommendation systems. So our main aim for this study was to study this phenomenon more closely and propose methods to reduce its impact. For our problem setting, we assume a user interaction session to consist of a sequence of articles of size n, where each article has a corresponding binary feedback label of either 1 or 0 to depict if they like the article or not. And we also additionally assume that each of these news articles is assigned to exactly one unobserved topic. And to simulate user partisan preferences, we assume a user's feedback label follows their political preference for that topic. For example, if a user prefers to read conservative articles on topic TFI, then the feedback label will be 1 for all conservative articles that belong to topic TFI and 0 for the liberal articles. The main phenomenon of interest occurs when a user has diverging preferences on two topics. So they prefer to read liberal articles on healthcare, but conservative articles on immigration. And this is a challenging case for the recommender, as not only are the topic assignments not observed, but also topics don't arrive uniformly at random. So the system, for example, the system may mostly observe healthcare articles and only a few immigration articles. And in this kind of setting, the recommender may incorrectly extrapolate that because the user prefers liberal articles on healthcare, they also prefer liberal articles on immigration, which can lead to poor recommendations as the recommender is biased towards showing politically homogeneous articles across the two topics. So to measure system setting in this system behavior in this setting, we assume to observe a training batch consisting of N1 articles from topic I and N2 interactions from topic J, where N2 is considerably smaller than N1. And we assume that a user has different political preferences for topic I and for topic J. And based on these interactions, we then train a content-based recommendation system on this topic pair, and then measure the accuracy of the recommender on a held-out sample of articles from both topics. And so in order to reduce this effect of cross-topic political homogenization, we leverage the recent advances in neural attention mechanisms and multitask learning, where in our first approach, we aim to reduce attention on topic-dependent polarized terms. For this, we use a fully connected network with the word attention layer that receives feature representations from BERT, transformer-based language model. And to accomplish this reduction in attention, we employ a two-step process where first we identify a candidate set of polarizing terms that are not topic dependent from our news article corpus. And after this, we augment the objective function to penalize attention on them and related terms. And in our second approach, we increase attention on topic dependent terms by using a multitask model that predicts both the article label as well as the masked word from the article headline. And the intention here is that this auxiliary task of predicting masked headline words will encourage the model to pay more attention to words that are specific to this article and that such terms are likely topic dependent. And we also consider a third model which combines both of these proposed approaches together. And for the data, for our data, we consider a news article dataset, which contains around 900,000 articles from 41 different news sources. And here, each article is associated with a political stance, so either as liberal or conservative. And we uniformly sample 100,000 of these news articles across the two stances. And as we need to simulate users with diverse political stances across topics, we need to assign topics to each news article. And so for this, we cluster our set of news articles into different set of clusters, where each cluster represents a topic, and we filter these out to ensure sufficient cluster size and such that each of these clusters contains an equal distribution of articles for both the liberal and conservative stance. And for our experiments, we measure the performance of our networks using a setting where 90% of the articles in the training and validation set are from a randomly sampled topic T of I, and 10% are from a randomly sampled topic T of J. Here, the small number of training examples from topic T of J makes this a challenging problem that's very similar to a cold start setting. And the test set is comprised of an equal distribution of articles from both topics TFI and TFJ. And next, we simulate user preferences such that their political preferences for topic TFI articles are the opposite of their preferences for topic TFJ articles. And we repeat experiments for 45 pairs of topics, where each run consists of a different topic pair, which are sampled from our list of discovered topics. And after with this, we then predict on the test set and compare the overall accuracy of each approach, as well as investigate how the accuracy varies by topic. And here our goal is to improve accuracy on topic T of J without harming accuracy on topic TFI. We also wanted to assess the ceiling of improvement that was actually possible. And for this, we fit a model we call topic oracle, which, unlike the other methods, is able to observe the topic assignment of each article. So in our results, we find that on average that our proposed networks tend to have higher accuracy for recommending topic TFJ articles compared to the baseline networks. And we also observe that there's an increase in accuracy across topic TFI recommendations as well. And we also find that the model that combines both proposed approaches together appears to do as well or better than each of the other methods in isolation. And finally, we also noticed that by comparing with the topic oracle models, the best of the proposed models approaches the accuracy of the topic aware oracle. We also investigated how the models perform based on the similarity between topic TFI and topic TFJ for a given topic pair. And for this, we use a simple method to quantify the overlap in predictive terms across two topics, where first we fit two logistic regression models, one per topic, and train them to predict the political stance of each article. We then select top terms from each of these classifiers and compute the Jacquard similarity to measure the overlap of each topic pair. So thus, topics are similar if they share terms predictive of political stance. And we can see the results in this graph where the trend lines are generated using Loess regression. While there is a noticeable variance across the topic pairs, we can still see that the largest gains occur in the middle region of the x-axis, where the topics are neither too similar or dissimilar. And this kind of hints at the fact that if topics are very different and they share few terms, then there's little opportunity for homogenization. And thus, we don't expect our models to provide much improvement. And while on the other hand, if the topics are too similar, then differentiating with them will prove quite difficult. So to conclude in this work, we identified a specific mechanism that can lead to political homogenization in news recommendation systems. And we proposed attention-based neural networks to reduce this behavior. And these proposed approaches reduce the impact of cross-topic political homogenization for simulated users with opposing political leanings across topics. And for future work, we plan to perform user studies to confirm the intensity of such homogenization and to better measure the impact of our proposed approaches. And we also want to experiment with a wider set of recommendation approaches to better understand the variation in algorithmic effects. And finally, we also want to perform algorithmic auditing to quantify the extent to which cross-topic political homogenization occurs in deployed real-world news recommendation systems. I think that's it. Yep, thank you.
Thank you very much. So we have a number of questions on this, and people are especially curious about your data set. So how did you make the political labels? Did you have human annotators? And if so, did they maybe introduce bias into the data set?
No, so the political stances for the articles are actually derived from the news source. So there's this organization called allsites.com that is a media bias rating. They assign media bias ratings for different types of news organizations. And so what we did was if a specific article was published by a specific news source, then the corresponding stance of that news source was taken to be the stance of that news article.
Okay, so for a provider, the complete set of articles would have one stance.
Yep, that's right.
Okay. Well, then we have a different question on diversifying news, which might lead to exposing the users to undesired news articles. Have you studied whether that would happen with your system, whether people get news they don't want to see actually?
I mean, it is possible if a person has very monolithic preferences, where they're like completely say just purely conservative, and the topics they follow are quite diverse. I think that is kind of possible, but yeah, I can't directly talk on that since I've not tried it out.
Okay, thank you for that. And then one final question about your clustering step. How
Yeah.
did you cluster the news articles by topic?
Yeah, for this, we just use simple k-means, but our study is not dependent on how the topics are discovered, so you could use any kind of techniques for this. You can use either LDA or anything that you deem is reasonable to cluster.
Okay, but in this case, you just
Yeah, I
used
just
the
use k-means.
k-means. Yeah. Okay, then let's thank the speaker again, and the rest of the questions you can answer offline. So now we are moving from news to music, and the next talk is given to you by Minyo Park, and it is about exploiting negative preferences in content-based music recommendation with contrastive learning.
Okay. Hi everyone, I'm glad to meet you. I'm Minju Park from Music and Audio Research Group, Seoul National University. The work I'll be presenting is about exploiting negative preference in content-based music recommendation with contrastive learning. So firstly, I'd like to introduce the motivation of this study. The naive motivation was very simple at first. For personalized music recommendation, we have to understand or explain the user's music taste. And then I came up with a question, which is easier to explain, musics I like or musics I don't like? Just simply thinking about it based on my experience, my answer was that it is easier to explain musics I don't like. So throughout this study, we focus on this hypothesis and we'll be finding some evidence in it. These are the two research questions that I want to show through this study. First, I want to find out what characteristics negative preferences have in terms of explaining music taste. And according to our hypothesis, that it is easier to explain the songs I don't like, negative preference in music taste has to have more distinct characteristics compared to the positive, and we'll see what happens. And secondly, I also want to see how applying negative preference will help improve music recommendations. So we'll be discussing the advantages of exploiting negative preference in music recommendations. Let's take a look at the existing studies. As a lot of you know, there are collaborative filtering and content-based methods in recommendation algorithms. And collaborative filtering can involve one's music taste in the latent space, but when it comes to explaining the music taste, the content itself has to be considered. So we'll be using the content-based method as the main framework of our study, of our model. But however, there's also a drawback that the content-based methods highly rely on similarity. So in our work, we'll be exploiting the user preference data along with the contents. We also want to focus on recommendation systems applying negative preference. There are existing works applying negative preference in recommendation systems, and in case of music recommendation, applying skipping behaviors might be an example. However, most of these studies conclude by proposing a novel architecture with increased performance. And improving the model's performance is important, but the fundamental analysis of why better recommendations have become possible is sometimes overlooked due to the focus on the engineering perspective. Therefore, in our study, we would like to focus on illuminating the specific roles of negative preferences compared to the positive preference. Now let's talk about our methodology for answering the research questions that we set up in advance. This is the overview of our model framework. And since we are on content-based music recommendation, we extract the features of the songs first. In order to focus on the identity of the music content itself, we adopted pre-trained models based on self-supervised manner to ease out our training procedure. We'll be using these three different feature extractors to evaluate the stability of our proposed method. Then we feed the extracted features in the contrastive learning stage. We differently condition positive and negative preference here in order to compare the final recommendation results. And in fact, this is the main part of our model, since the main goal of our study is to understand the effects of negative preference through the comparison of recommendation models in which preferences are differently conditioned. I'll explain in more detail how we applied preferences differently. So we designed the contrastive learning models with three different training strategies, exploiting preferences of both positive and negative, positive only, and negative only. For convenience, I'll be calling them CLEP PN, CLEP P, CLEP N, and respectively. As it is seen in the contrastive loss formula, contrastive learning is basically trained to embed data pairs with the same label close together and embed the data pairs with different labels far away. And in our case, we will be conditioning the way we label the data pairs according to the three models. For CLEP PN, which exploits positive and negative preference, positive pairs and negative pairs are considered as the same label, so that the model will embed these pairs of songs close together and embed the positive pairs of songs far away. And for CLEP P, we're gonna consider the positive pairs as the same label, and vice versa for CLEP N. And in fact, this is the model we would really like to focus on, since this is the one exploiting negative preference. So if we think of a user's music taste as a complex distribution of songs the user likes and dislikes, we were interested in which of these three models most similarly simulates the distribution. And lastly, with the embedding after the contrastive learning, MLP layers are added and trained to match the ground truth of whether the user likes or dislikes the song. So with this framework, we did the experiments, and to train and evaluate our model, we needed a personalized user preference data set. So we conducted a web-based survey asking participants about their music preference. We recruited 24 volunteers, and they were asked to listen to about 200 music clips and answer whether they liked or disliked each song. So we were able to obtain 24 individual personalized music preference data set and 200 preference data per person. So we divided them into a training set and a test set, then trained the models with the training set and assessed their performance on the test set. For the evaluation, we chose accuracy, precision, recall, AUROC, and false positive rate as our evaluation metrics. These are like common metrics used in classification tests, but in our case, precision and false positive rate were considered somewhat special. What these two have in common is that false positives are involved. Then what's so special about this false positive is that false positives have more significance in recommendation tasks than in general classification. Like for instance, when it comes to music recommendation, false positives indicate the recommended songs which the user dislike, while the false negatives indicate the not recommended songs which the user like. So from the user's point of view, false negatives are almost impossible to recognize. On the other hand, false positives will definitely have a negative effect on the user experience. So like this, false positives are a clear concern in recommendations, and there are several studies conducted supporting this. So precision and false positive rate will help analyze the practical utility of a music recommendation system. Now the conclusion part. We evaluated our models by having our trained models predict the user's preference for every test set of our individual preference data set. The experimental results were analyzed through the Friedman test. Among the 5 evaluation metrics, accuracy, recall, and false positive rate showed statistically significant differences in models regardless of the music feature extractors. And in order to verify specified relationship between the models for these 3 evaluation metrics, Wilcoxon-Sign rank tests were performed as the post-hoc analysis. So if you see this, although the relationship between CLEP PN and CLEP P was slightly different depending on the musical feature extractors, but the CLEP N, which was the model we want to focus on, outperformed the other 2 for accuracy and false positive rate, while showed the lowest recall among the 3. So to sum up these results, focusing on the CLEP N showed the best accuracy, the best false positive rate, but the poorest recall. False positive rate is sometimes called an anti-metric for recall, which is a metric aware of the irrelevant items returned by the recommendations. And previous studies say that when distinguishing recommendation systems with similar relevance, anti-metrics are more valuable than classical metrics. So considering this point, we would like to insist that the fact CLEP N is showing a high false positive rate is still a strong evidence of its potential to be utilized in recommendation system despite this poor recall. So based on these results, let's get back to the research questions we wanted to answer. So for the first question, since we have shown that CLEP-N had the highest accuracy, we can say that CLEP-N simulates the true distribution of music taste most similarly among the three. These are the examples of the embedding space of the trained model